Bismillahirrahmanirrahim. Hello everyone. I hope you are all doing well. I welcome you all to the class of Elementary Number Theory by David M. Burton. Our discussion is continue on chapter number 5, Fermat's Theorem. In today's lecture, we will discuss one of the core topic of this chapter, and you can say this is the core topic of number theory, pseudoprimes. So we start our discussion from Fermat theorem. How can we define Fermat theorem? The statement of Fermat theorem is Fermat theorem, or simply you can say this is the Fermat Little theorem. Fermat Little theorem. This theorem says that if P is prime and A is an integer, such that A and P are co-prime, mean to say their GCD is 1. Then this theorem says A raised to power P minus 1 is always congruent to 1 modulo P. So this is the statement of Fermat Little theorem. This theorem hold in case of prime number, but if the integer is any composite, mean to say if power this exponent or this modulo is a composite integer, then theorem may not hold. For example, if we take n is equal to 4 and a is equal to 3, then according to this theorem here, a raised to power p minus 1, now I am taking a composite integer n. This becomes n minus 1, that is 4 minus 1, which is equal to, what is a? A is 3 raised to power 3, which is equal to 27, and 27 is congruent to 1 modulo 4. So for this choice, when you take a is equal to 3 and n is equal to 4, this theorem hold. But if you take n is equal to 9 and a is equal to 2, this becomes a raised to power 8, that is equal to 2 raised to power 8, and this is congruent to 4 modulo 9, which is not congruent to 1 modulo 9. What is the definition of congruency? We say two integers a and b are called congruent if a and b are congruent with modulo n if n divides their difference a minus b. So we can notice that when you take 2 raised to power 8, this is congruent to 4 with modulo 9. For you can verify that here 2 raised to power 3, this is equal to 8, and 8 is congruent to minus 1. The number after the congruency sign shows the remainder. When you divide 2 raised to power 3, that is 8. When you divide 8 by 9, the remainder will be minus 1. So 2 raised to power 3 is congruent to minus 1 modulo 9. To make the power 2 raised to power 8, we are taking square on both sides. This becomes 2 raised to power 3 whole power 2. This is minus 1 square. Minus 1 square is equal to 1 modulo 9. That is 2 raised to power 6 is congruent to 1. Multiply on both sides with 2 square, that is 4. This is equal to 2 raised to power 8 is congruent to 4 after multiply with 4 on both sides. That is 2 square. This is modulo 9. So from this example you can notice that Fermat Little theorem may not hold in case of a composite integer. Now the story of Pseudoprime start. 2500 years before, Chinese mathematicians claimed that what is the claim? They claim that an integer n is prime if and only if n divides the number 2 raised to power n minus 2. In other words, this is the necessary and sufficient condition. When n is prime, then it must divide 2 raised to power n minus 2. And if a number divide 2 raised to power n minus 2, then that number will be prime number. And their claim is reliable for all integers less than or equal to 340. For example, if you take n is equal to 3, that is the or you take if n is equal to 2, that is the first prime. You can check that 2 divide 2 square minus 2. 2 square means 4, 4 minus 2, that is 2, and 2 divide 2, this is true. If you take n is equal to 3, again you can notice that 3 divides 2 raised to power 3 minus 2. 2 raised to power 3, this is 8, 8 minus 2, this is 6, and 6 is divisible by 3, this is also true. If you take n is equal to 5, you can check that 5 divide 2 raised to power 5 minus 2. 2 raised to power 5 means 32, 32 minus 2, this is 30, and 30 is divisible by 5. So their claim is true for all those integers which are less than or equal to 340. In 1819, it was discovered that their claims fail when we take when we take n is equal to 341. This number fails their claim. You can notice that this number is not a prime number, this is a composite number. This is the product of two integers 11 and 31. So it means this number is a composite number. But still this number divides 2 raised to power n minus 2. That is 341 divides 2 raised to power 341 minus 2. This shows that their claim is not true. Because they said that only the prime number divides 2 raised to power n minus 2. But we find a composite number that still divides 2 raised to power 341 minus 2. And we will prove this at the end of lecture. Actually, this is our main target, and that will shows 341 is a pseudoprime. So now we discuss the proper definition of pseudoprime. If we convert this expression in the form of congruency, what is the definition of congruency? A number A is congruent to B modulo n if n divides A minus B. And if n divide A minus B, then two numbers are congruent. It means when you say two numbers are congruent, then you can divide them in the form of divisibility as n divide their difference. And if n divide their difference, it means they are congruent. So if you apply this concept on this expression, you can write it as n divides 2 raised to power n minus 2 means 2 raised to power n minus 2 raised to power n is congruent to 2 modulo n. Or you can say, after dividing by 2 on both sides, this becomes 2 raised to power n minus 1. This is congruent to 1 modulo n. When n and 2 are co-prime, then we can divide on both sides by 2. So if you compare this definition with the Fermat Little Theorem, this is the Fermat Little Theorem. According to this definition, here A is 2 and P is equal to N. And actually this is the definition of the pseudoprimes. So now I am writing the proper definition of the pseudoprime. Okay. A composite integer n is called pseudoprime. A composite integer n is called a pseudoprime if n divides 2 raised to power n minus 2. This is the definition of pseudoprime given in the David book. Or this definition in the form of congruency, you can write it as, or you can say 2 raised to power n, if 2 raised to power n is congruent to 2 modulo n integer n, composite integer n, then n is a pseudoprime. Or further you can write it as 2 raised to power n minus 1 is congruent to 1 modulo n. So this is the proper definition of a pseudoprime given in the textbook of David and Burton. Further you can say that, or we can also write this definition as, a composite integer n is called pseudoprime. A composite integer n is called a pseudoprime if it satisfies the Fermat Little Theorem for base A is equal to 2. Now there are something important that you must notice. This is the definition of a Fermat. This is the definition of pseudoprime only for base 2. This is the not general definition of pseudoprimes. In David and Burton, we find only the definition of Fermat pseudoprime because these integers just satisfy the Fermat Little Theorem. It means the concept of the base other than 2 also exists. Mean to say, a composite integer n is called pseudoprime for any base A. Now I am writing the most general definition of pseudoprime beyond the book of David and Burton. A composite integer n is called pseudoprime for any base A, where A and n are co-prime, that is their GCD is 1. If this integer n satisfied the Fermat Little Theorem criteria, that is A raised to power n minus 1 is congruent to 1 modulo n. So this is the most general definition of pseudoprime that is not available in the book of David and Burton. David just discussed the definition of pseudoprime for base 2. That's why we can say this definition particularly as the Fermat pseudoprime for base 2. It means on the base of the name of mathematicians, the concept of Wilson pseudoprime also exists. Strong pseudoprime, Jacobi pseudoprime, or Carmichael number, etc. These pseudoprime also exist. But because we are only focusing on David and Burton book, so we will just discuss the concept of Fermat pseudoprime. So So this is the most general definition of a pseudoprime. I am again repeating. A composite integer n is called pseudoprime for any base a such that a and n both are the coprime if a raised to power n minus 1 is congruent to 1 modulo n. If we restrict a is equal to 2, then it becomes the Fermat pseudoprime for base 2. In Fermat pseudoprime, there exist other bases. For example, Fermat pseudoprime for base 3, Fermat pseudoprime for base 5. The main concept is that you can find the Fermat pseudoprime only for those integers which are coprime to n, Mean to say, there is no need to find the Fermat pseudoprime. For example, if n is equal to 100 and you want to check is 100 is a pseudoprime for base a is equal to 4, this is not the requirement, because n and a both are not coprime, or both are not relatively prime. Now I am going to discuss the most important example of Fermat pseudoprime. The first Fermat pseudoprime is n is equal to 341 for base a, for base 2. Our question is, show that n is equal to 341 is a base 2 pseudoprime. What we have to show? We will show that 2 raised to power 341 minus 1, which is equal to 2 raised to power 340. This should be congruent to 1 modulo 341. This is our target to show. So when you have to prove a composite integer for pseudoprime, the first step is that we will make its prime factorization. The prime factorization of n is equal to 341 is 31 and 11. So this is the product of two distinct primes. First prime is 31 and second is 11. Now I will use the Fermat Little Theorem separately for both of these prime. By Fermat Little Theorem, for P1 is equal to 31. Substitute P is equal to 31 here, and A is equal to 2. Although it is not mentioned that which base we have to take, but when the statement is just that n is equal to 340, show that n is equal to 340. This is also given. Base 2 is also given. But if in case when base is not mentioned, you will always use the base 2. So put A is equal to 2 and P is equal to 31 here. So for this prime number, the first congruence is 2 raised to power 30 is congruent to 1 modulo 31. This is the first congruence that I will use. Similarly, for Fermat Little Theorem for second prime, that is P2 is equal to 11, we have 2 raised to power 10. This is congruent to 1 modulo 11. Say this is 1 and this is 2. I have to show that 2 raised to power 340 is congruent to 1. So I will consider 2 raised to power 340 and I will use both of these congruence simultaneously, and I will show that 2 raised to power 340 is congruent to 1 modulo 341. So firstly I use 2 raised to power 30, 2 raised to power 10. Firstly I use 2 raised to power 10 and I make 2 raised to power 340 here. Okay. consider 2 raised to power 340. This can be written as 2 raised to power 10. I am going to use 2 raised to power 10 here. So what should be what should I have to write here outside the 2 raised to power 10? This is simply, if you divide 3 raised to power 40 by 10, this gives 34. So 2 raised to power 340 can be written as 2 raised to power 10 whole power 34. Now using 2 raised to power 10 is congruent to 1. So I can replace 2 raised to power 10 with 1 and whole power 34. 1 raised to power 34, this is simply is equal to 1. So it means 2 raised to power 340 is congruent to 1 modulo 11. Say this is 3. Again we will use the congruous 1. Okay. Next consider the first congruence. 2 raised to power 340, this is equal to 2 raised to power, what was here, this is 2 raised to power 30, this is equal to 2 raised to power 30 here. Okay, 340 is not completely divisible by 30. So firstly we divide 340 by 30. This is 3 11s are 33 and the remainder is 10. So we can write 2 raised to power 340 as by Euclidean algorithm, this can be written as 30 into 11 plus 10. Further you can write it as 2 raised to power 30 whole power 11 into 2 raised to power 10. Now using congruous 1, according to congruous 1, 2 raised to power 30 is equal to 1. So this becomes 1 raised to power 11 into 2 raised to power 10 with modulo, what is modulo? Modulo is 31. So when we utilize here congruous 1, then we will take the modulo here. So this is congruent to 1 raised to power 11, this is 1. This is congruent to 2 raised to power 10, sorry, modulo 31. Next we have to calculate 2 raised to power 10 modulo 31. 2 raised to power 10 modulo 31. Okay. Next we find 2 raised to power 10 modulo 31 as 2 raised to power 5. This is equal to 32. This is equal to 32. And when we divide 32 by 31, what is the remainder? The remainder is 1. It means 32 is congruent to 1 modulo 31. This implies 2 raised to power 5 whole square. This is taking square on both sides. This becomes 1 square, and 1 square is equal to 1 modulo 31. This shows 2 raised to power 10 is congruent to 1 modulo 31. Substituting this value of 2 raised to power 10, that is congruent to 1 here, this becomes 2 raised to power 340 is congruent to 1 modulo 31. This shows that 2 raised to power 340 is congruent to 1 for both of prime factors 31 and 11. Next, lastly I will use the corollary of Chinese remainder theorem. That is, what is the corollary? The corollary says if suppose x is congruent to a under modulo m1, similarly again x is congruent to a with modulo m2, and this procedure is continue for k modulo each time x is congruent to a. Finally, we can write as x will be congruent to a modulo L, where L is the LCM of all of these integers m1, m2, mk. So using this scenario for congruence 3 and 4, in 3, 2 raised to power 340 is congruent to 1 under modulo 11, and again 2 raised to power 340 is congruent to 1 modulo 31. So my m1 is 11, the first modulo, and m2 is 31. So what is the LCM of 11 and 31? As 11 and 31 both are prime number, so their LCM will be just their product, and their product is 341. So after referencing this corollary and by using 3 and 4, we can say that 2 raised to power 340 is congruent to 1 modulo their LCM, that is 31 and 11, which is equal to modulo 341. So this shows that 341 is a Fermat Pseudoprime for base 2. Similarly, the next Pseudoprime is 561. The next Pseudoprime is 561. Next, we show that 561 is a 561 n is equal to 561 is a Fermat Pseudoprime for base 2 also. What is the procedure? Firstly, we will make its prime factorization. Its prime factorization is simply 3 into 11 into 17. This is the prime factorization of 561. There are the three distinct prime factor here. We will use Fermat Little Theorem for each of these prime factor. When we use the Fermat Little Theorem for the first prime number, that is 3, P1 is equal to 3. According to Fermat Little Theorem for base 2, we have 2 raised to power 3 minus 1. This is congruent to 1 modulo 3. That is 2 raised to power 2. This is congruent to 1 modulo 3. Say this is congruence 1. When your P2 second prime number is 11, this implies after applying Fermat Little Theorem, this becomes 2 raised to power 10 is congruent to 1 modulo 11. Similarly, when you take third prime P3 is equal to 17, this becomes 2 raised to power 16 congruent to 1 modulo 17. Now what I have to show? I have to show that 2 raised to power 560 is congruent to 1 modulo 561 here. So consider 2 raised to power 560 for all of these congruences 1, 2 and 3. Consider 2 raised to power 560. This can be written as 2 raised to power by using the first congruence. Here we have a power 2 raised to power 2. So we can write it as 2 raised to power 2 whole power. This will be 280. Because 2 completely divide 560, there is a zero remainder here. So we can write as 2 raised to power 2 into 2 raised to power 80. By using the congruence 1, 2 square is congruent to 1. This is congruent to 1 modulo 3. This is congruent to 1, and this will be 1 whole power 280, and 1 whole power 280 is 1. So this is the 2 raised to power 560 congruent to 1. Say this is 3. This is 4. Next, again using second congruence. In the second congruence, we have 2 raised to power 10. So again we can write it as 2 raised to power 560 is 2 raised to power 10 whole power 56, and this is again congruent to 1 modulo 11. Lastly, when you use 2 raised to power 2 raised to power 560, this is congruent. This is equal to 2 raised to power 16 whole power 35. 35 into 16 is 560. This is congruent to 1 modulo 17. So again, using the corollary that I have discussed, in each case 2 raised to power 560 is congruent to 1. So finally we can say that 2 raised to power 560 is congruent to 1 under modulo The LCM of 3, 11, 17, because each of moduli is a prime number, so their LCM will be just their product. So this is equal to 561. So this shows that 561 is also a Fermat Pseudoprime for base 2. So I hope now you have a clear understanding about Pseudoprime. In Pseudoprime, you notice that base uh, maybe other than is equal to maybe other than 2. In the next lecture we will discuss that if some number is a pseudo prime with respect to some base, then it is not necessary that with respect to any other base it is also a pseudo prime. So the next lecture will be very interesting. So I hope now you have a clear understanding about today's discussion. If you find my lecture helpful, kindly like, share and subscribe my channel. See you in the next lecture. Take care. Allah Hafiz.